Welcome to the deep dive. Today, we're venturing into, the heart of our solar system, really, looking at the sun.
Yeah, specifically a new study that's giving us a much sharper picture of its chemical makeup.
And we're focusing on helium, element number 2, the second most abundant thing out there in the sun after hydrogen.
Exactly. And this is particularly relevant for you listening, especially those of you preparing for the UPSC exams.
Right. Understanding these kinds of fundamental scientific steps forward, especially when they come from Indian institutions like the Indian Institute of Astrophysics or IIA, it's really valuable.
It absolutely is. It shows how dynamic space science is, that interplay between physics, astronomy, it's all connected.
And the information we're discussing today, it's based on research published in the Astrophysical Journal, but importantly, it's been highlighted by the Press Information Bureau, the PIB.
So our mission, if you like, for this deep dive is to unpack why measuring helium in the sun's the photosphere, has been so difficult.
And then explore this innovative new technique the IIA researchers have come up with.
Finally, understand what their findings actually mean for our understanding of the sun. Sound good?
Sounds great. Okay, so let's start with the basics. Figuring out what the sun is made of. On the face of it, seems like Job 1 for solar scientists, right? But helium, specifically in that outer visible layer, the photosphere, it's been tough to pin down.
It really has. It's quite fascinating, actually. Helium in the photosphere is, well, a bit spectroscopically shy.
Spectroscopically shy. Meaning?
Meaning it doesn't easily create those distinct spectral lines, the unique barcodes of light that elements emit or absorb, not in the conditions of the photosphere anyway. So we can't just see its signature easily there.
Ah, okay. So unlike other elements that kind of wave a flag saying, here I am,
Sure.
helium is more subtle in that layer.
Precisely. Which meant that for a long time, scientists had to get creative, relying on indirect methods to estimate how much helium was there.
Indirect methods? Like what? Are we talking educated guesses or something more solid?
Oh, more solid than guesses, but definitely indirect. One way was to look at hotter stars, where helium does show stronger spectral lines, and then sort of extrapolate back to our sun.
Okay, assuming our sun is similar enough in some ways.
Right. Another approach was to measure helium in the sun's outer atmosphere, the corona, or in the solar wind that streams off it.
Further out from the photosphere itself.
Exactly. Or they'd use helioseismology, studying the waves, the vibrations traveling through the sun, kind of like how seismologists study earthquakes on Earth. Those waves are affected by the sun's composition, including helium.
But none of those are actually measuring helium in the photosphere directly.
That's the crucial point. They all involved assumptions, extrapolations. They weren't looking right at the source layer in the way we'd ideally want to.
Which brings us to this new study from the Indian Institute of Astrophysics. It sounds like they found a way around helium's shyness.
They have indeed. It's a really novel method, originally developed by B.P. Hema and Gajendra Pandey at IIA. And this latest study applying and validating it was led by Satyajit Moharana, who's also at IIA, but doing his PhD work with Kasi in South Korea, working alongside Hema and Pandey.
So what's the trick? If helium isn't talking, who are they listening to instead?
They decided to eavesdrop on some other elements that are quite chatty in the photosphere, specifically neutral magnesium, that's MgI, its molecular form, bonded with hydrogen, MgH.
Magnesium hydride. Okay.
And they did the same for neutral carbon, Ci, and its molecules, CH, and even the diatomic C2 molecule. They looked at the spectral lines of all of these.
Right, so magnesium and carbon lines are visible in the photosphere, but how does measuring them tell you about helium? That feels like a leap.
It does, but here's the clever connection. The core idea is consistency. The amount of magnesium you calculate just by looking at the magnesium atom lines, MgI, must agree with the amount you calculate by looking at the lines from the magnesium hydride molecule, MgH. The physics demands it. Same logic for carbon and its molecules.
Okay, that makes sense. Consistency check. But where does helium fit in?
It fits in because of hydrogen. Hydrogen is, the overwhelming majority element in the sun.
Right, number one.
And the formation of these molecules, MgH and CH, obviously depends on how much hydrogen is available to bond with the magnesium and carbon.
Ah, okay. The amount of ingredients affects the final product.
Exactly. Now, since helium is the second most abundant element, the ratio of helium to hydrogen fundamentally affects how much hydrogen is left over, or available in the right conditions for everything else, including forming these molecules.
I see. So by carefully measuring the atomic lines and the molecular lines of magnesium and carbon,
And demanding that the abundances calculated from both match.
you indirectly constrain how much hydrogen must be there, which in turn tells you how much helium there must be, because they make up almost everything.
You've got it. It's like solving a puzzle by making sure all the different pieces related to magnesium and carbon fit together perfectly, and the only way they can fit is if you assume a specific amount of helium affecting the overall environment.
That's really elegant. So they're using these other elements as probes for the helium abundance.
A very elegant spectroscopic probe, yes.
Now, I imagine this isn't just a quick look. You mentioned spectral lines. How do they analyze these precisely? The paper mentions some specific techniques.
Yes. After doing very careful calculations about how these spectral lines are actually formed, which is complex in itself, they primarily use two techniques, equivalent width analyses and spectrum syntheses.
Okay, can you break those down a bit?
Sure.
Oh.
Equivalent width analysis is basically a very precise way to measure the strength of a spectral line, how dark or deep it is, which tells you how much light is being absorbed or emitted by that specific atom or molecule.
Measuring the barcodes accurately.
Exactly. And spectrum synthesis is like building a theoretical model of the sun's spectrum based on physics and assumed abundances of elements, and then comparing that synthetic computer-generated spectrum line by line, detail by detail, with the actual observed spectrum from the sun.
To see how well the model matches reality.
Precisely. You tweak the abundances in your model, including helium, until the synthetic spectrum perfectly matches the real one. It's incredibly detailed work.
Okay, so that's the how. Now, why is getting this helium number right so important? The study mentioned photospheric opacity. What's that, and why does helium matter for it?
Opacity is just a measure of how difficult it is for light, for radiation, to travel through a material. Think of it like fog-high opacity means light struggles to get through.
Right, so the sun's photosphere has an opacity.
Yes, the gases there impede the flow of energy outwards. And the main things doing the impeding are the most abundant elements, hydrogen and helium. Their atoms and ions absorb and scatter photons.
So the amount of hydrogen and helium directly affects how easily energy escapes the sun's visible surface.
Fundamentally, yes. Moharana used a great example in the work. Imagine if there was more helium than we thought.
Okay.
That would mean there has to be less hydrogen, right? Because they make up almost everything.
Less hydrogen.
Less hydrogen means fewer atoms overall to block the light, so the photosphere would become less opaque, more transparent in a way.
Right, less stuff in the way. Makes intuitive sense. But wasn't there a complication with those molecules they were studying, the MgH and CH? Something counterintuitive?
Ah, yes. This is where it gets subtle. If you have less hydrogen overall, because you assumed more helium, you'd also have fewer hydrogen atoms available to actually form the MgH and CH molecules.
So you'd expect the spectral lines from those molecules to get weaker.
Exactly. But remember, the overall opacity also decreased. So the background light against which we see these lines changes too. It turns out that to match the observed strength of the MgH and CH lines in a less opaque environment with less hydrogen available to form them, you'd actually need to assume there was more underlying magnesium or carbon to begin with to compensate.
Whoa, okay. So changing the helium assumption messes with things in complex ways.
It does. And that's why their method, demanding consistency between the atomic MgC and molecular MgH-CH views, is so powerful. It navigates these interconnected effects.
It forces the whole picture to make physical sense simultaneously. Very neat. So after all this careful analysis, what did they find? What's the number for the helium to hydrogen ratio?
The result that came out consistently from their analysis was a helium to hydrogen abundance ratio, HH, of approximately 0.1.
0.1. So roughly 1 helium atom for every 10 hydrogen atoms in the photosphere.
That's the essence of it, yes.
Now, is this number bombshell? Does it completely change our models of the sun, or does it align with what we thought?
This is perhaps the most satisfying part of the study. The result, obtained through this completely independent, direct spectroscopic method for the photosphere, is in remarkable agreement with the values derived from helioseismology, from studying those internal solar vibrations we talked about earlier.
Wow, okay. So two very different methods, one looking at the surface light, one probing the deep interior, are giving the same answer for the helium abundance.
Pretty much, yes. Which gives us enormous confidence that this He ratio of about 0.1 is pretty spot on.
So it's not overturning the established value, but it's confirming it with a completely new and arguably more direct photospheric measurement.
Exactly. It validates both the previously accepted value and the power of their new technique. It confirms that the standard solar models, which have been using roughly this ratio, were fundamentally on the right track regarding helium in the photosphere.
Which feeds back into understanding that opacity correctly and how energy gets out of the sun.
Precisely. Getting that helium abundance nailed down more accurately allows for more refined models of the photosphere, better understanding of energy transport, and ultimately a clearer picture of how our star works.
Okay, so wrapping this up, what's the core takeaway message from this deep dive for us?
I think the key point is that researchers, specifically at India's IIA, have developed and successfully used a really smart new technique to directly measure helium in the sun's photosphere.
Something that was hard to do before.
Very hard. And their findings confirm the existing estimates, particularly those from helioseismology, giving us much stronger footing for our understanding of the sun's composition and physics, especially that tricky photospheric layer.
And connecting back to you, our listeners, particularly the UPSC aspirants, seeing how fundamental science like this progresses is crucial.
Absolutely. It's about understanding the building blocks of our universe, how we figure these things out, the ingenuity involved. It enhances that scientific literacy that's so important.
And it highlights the contributions of Indian science institutions on a global stage. This kind of work, reported via PIB, is exactly the sort of current scientific development worth knowing about.
It really is. It also prompts a wider thought, perhaps.
Yeah.
Well, if a long-standing challenge like measuring photospheric helium can be tackled with a new technique, what other firmly held assumptions in astrophysics might be revisited or refined as our tools and methods get even better?
That's a great point. Our understanding is always evolving as our ability to observe and analyze improves. Food for thought indeed.
Definitely.
Well, if you found this exploration of solar helium insightful, especially for your UPSC prep or just out of curiosity, please do give us a like and subscribe for more deep dives into important topics.
And if you have questions, drop them in the comments below. We'll do our best to address them.
Remember, all the details we discussed today stem from that research highlighted by the Press Information Bureau, PIB. Thanks for joining us on the deep dive.
Until next time, keep looking up.